So it's actually much more correct to say that there are two forces there, and they just happen to, the torques and forces tend to balance. Just a quick clarifier. So I've borrowed from our Giancoli textbook a problem-solving checklist, or list of things you should try when you're solving a statics problem. So I'm going to try to break this down. I'm going to make this available to you, of course. We're going to try to break this down and make it easy to use. We'll do an example using this checklist. So the first thing we do is you pick an object and draw a free body diagram for it. And then you're going to pick a convenient coordinate system. We'll talk all about that. Then you're going to use letters to represent the forces. Then you're going to deal with the torques. Remember, those are conditions for equilibrium. You're going to apply the first condition, which is where the forces are equal to 0, and the torque condition, where all the torques sum up to be 0. Here we're also going to talk about some of the difficulty with picking direction for torque, and then finally you solve. So what's cool about this is because there are so many equations that you're going to be using, you can solve for all kinds of different things. I'm going to quickly clarify from my original explanation of static equilibrium. We're only going to be using x and y. We're not going to be doing things in 3 dimensions. That makes things exponentially more complicated. So we'll pause that for right now. We're just going to be doing the total forces in the x and the y and the torques. All are going to equal 0 because the thing is going to be in equilibrium. So in some chicken scratch, I've translated that over, and I'll let you pause so you can copy it. But let me just quickly run back through those. So we're going to have a situation. You're going to first pick an object and draw a free body diagram for that thing. You're going to really do one object at a time. We'll show what that looks like. It doesn't end up mattering in a lot of cases. Just pick a thing and draw the free body diagram for it. Next, you're going to choose convenient coordinate system. You're going to break the force vectors into components using trig if needed. So if you see an angle, here's where you're going to be breaking that down. You also want to pick a convenient coordinate system. So if we're on a ramp or anything like that, you'll want to orient your coordinate system accordingly. Next, you will use the letters, using letters for unknown forces. You're going to set up the equilibrium equations in both the x and in the y. So that should feel pretty familiar. We've done a lot of that in the past, taking a free body diagram and using that to help us set up Newton's second law in both the x and y. Finally, in terms of setting it up, then you'll choose a rotation point. You want to pick a smart one. We'll talk about that. Often you'll want to pick one that's right at the fulcrum as an example. That will eliminate a torque. We'll again discuss that. It doesn't matter which one you pick, but you can make your life easy by picking a smart one. And then you're going to assign a plus and minus direction to the rotation. Usually that will be counterclockwise and clockwise respectively. And then you'll set up the equilibrium equation for torque, which is again is that the sum of the torques sums to 0. And then finally you're going to solve for whatever you want. What we've got here is kids sitting on a teeter-totter, and we're going to try to find the location x where kid B can sit, and for everything to work out fine for us to stay in static equilibrium. So I'm borrowing this question from the same textbook. It says a board of mass 2 kilograms. That's important. The board actually has mass. We'll discuss. It serves as a seesaw for 2 children, shown in figure 9.7a. That was the picture I just showed you. Child A has a mass of 30 kilograms and sits 2.5 meters from the pivot point P, which is where its center of gravity is. And at what distance from the pivot X must child B with a mass of 25 kilograms place herself to balance the seesaw? Assume the board is uniform and centered above the pivot. So we are going to follow these steps. We'll start by drawing, and we're going to follow those 5 steps to see if we can find out where this kid needs to sit. So I've got my drawing. We want to know where the kid who's 25 kilograms can sit. Now, this is the thing that we've done in the past by just using torques and things of that nature. I want to use this as a nice example to get us started. We are lucky here. The weight of our board actually acts on the point. That does make life easier. Let's actually run through the steps. So step 1 is pick an object, draw a free body diagram for it, just one at a time. So it actually doesn't matter, but we're going to pick the board to be our free body diagram. So I'm going to put this here. This is free body diagram of the board, and we're going to simply label all the parts of it. Now, it's going to be really helpful in a bunch of cases to draw the center of gravity, so I'm just going to put CG for center of gravity. It's right at the middle. Now, its weight will act at that point, as we discussed. So I'll just put mg there. And then you've got the weight of both kids acting down. So one of the kids acts like this. Let's call that mag. That would be the weight of the kid. You've got the weight of the other kid. We'll call that mbg. And then finally, because we need this to be balanced in the y direction, there's all those forces acting down, the weights. So that means we need a fairly substantial normal force. I'll just put a capital N there. And so far, we've done step one. We've drawn a free body diagram for our forces. The second thing is to choose a convenient coordinate system. We need to break the forces into vectors if we need to. So there's no angles here. Let's pick, and actually you might have seen it in the picture earlier, we're going to pick a coordinate system. Up is going to be in the y direction, and x is going to be like that. A lot of times this is going to be the orientation that we'll go with, but it'll depend, of course, on the situation. We'll address that as needed. Next, it says, using the letters for unknown forces, set up the equilibrium equations for force in the x and in the y. Now, for this part, we can simply ignore forces in the x direction, and we'll just simply go to the forces in the y direction equaling 0. Now, we're kind of skipping the step where we say, you know, Fy equals ma in the y, and that equals 0. We're skipping over that, and this is going to be the condition because it's in static equilibrium. So this should feel familiar, though it is a little bit different. So what we need to do is we just add in the forces like we've always done from our free body diagram. So this would be N minus, it doesn't really matter what order we go in. Why don't we go minus mag, so that's the force from this one, minus just the mass of the thing, the mass of the board, mg, minus mb in the times g. That all equals 0. Now the next step says choose a rotation point, a smart one, and assign the clockwise and counterclockwise directions. So we've actually already done that. I chose a smart place for it to rotate. Actually, the problem did, by having the weight act right at the pivot point. So what I mean is I can pick my pivot point. I'm going to say it's right here. And the reason for that is that two of my forces act at that pivot point. Now, I could have picked a pivot point over here at the edge, but now I've got 1, 2, 3, 4 torques. By picking the pivot point to be here, I've got just 2 torques. In other words, these two have a lever arm of exactly 0. Remember, torque is force times distance. These two have 0 distance away from the pivot point. It's going to end up making my life easier. So again, we're going to do step 4, which is to set up the sum of the torques is equal to 0. I need to pick a positive and negative direction. So I'm going to pick this torque would cause it to rotate in this direction. I am going to call that the negative direction. That's the clockwise direction, traditionally considered to be the negative direction. And I'm going to pick a positive torque from this one in the counterclockwise direction. It doesn't really matter, but I'm just going to go with those. Now, keep in mind that these torques are happening, this one is happening a distance of 2.5 meters away, and this is happening some unknown distance x away. Let me zoom in a little bit so we can see that better. So what we'll do is we'll set up the second law, but for torques, and we're going to do it starting with the positive. So we'll say this is ma times g times the distance, 2.5 meters. And then it's minus, because it's in the opposite direction, minus mbg times x. And that all sums up to be 0. So these are the torques from the x and y. Notice I've left out the normal force times 0 meters, because that torque has 0 distance. So it doesn't even exist. And the same with the weight of the board as well. So we have got set up here our condition for equilibrium in the forces. We've got our condition for equilibrium in the torques. And we're on our last step, solve for what you want. So what we really, really want is we would like to have that x. So in this case, what we want is where can the kid sit so that everything's balanced. And if you look carefully, we actually already know MA, that's 30 kilograms. We know G, that's just 9.8 meters per second squared. We're told this distance that the other kid is sitting, and we can solve this for X. So I'm going to show you that, and then we'll talk about why we didn't need this equation in this particular case, but then why not? We'll go ahead and actually use that equation. Okay, so to solve this, I'm going to first add mgb times x to both sides, so we'll have mag times 2.5 meters, that equals mbg times x. Now we can cancel our g's, and to solve for x, we simply divide by mb, so x is going to be ma times 2.5 meters divided by mb, so x is going to end up being 30 over 25, both kilograms, times 2.5 meters. So this ends up just being the ratio. It's proportional, should seem very familiar. Where should the kid sit? The answer ended up coming out to 3 meters, which makes sense. She's going to have to sit farther away because she weighs less. Now, so that answers the question. We did all 5 steps. It got us to what we wanted. Now, we didn't need, for various reasons, because of what we wanted to know, we didn't need to know, actually have to set this up, but I want to show you why you might set it up as an example. Maybe you want to know how much how much force this board has to exert to keep it up. And all that would be is the normal force. So in this example, let's just invent a question. What is the normal force exerted by the board? So all you would do is actually just solve for n. So the answer would be n is mag plus mbg plus m. Remember m here just being the weight of the board. I'm going to factor out a g, and then we'll plug these in. So 30 kilograms plus 25 kilograms. The weight of the board was 2 kilograms. And we end up with the normal force from the board pushing up to make this whole situation possible is about 7,400 newtons worth of force. So the normal force, Fn, would be equal to roughly 7,400 newtons. So that was an explanation of how to solve statics problems and us running through an example. Thank you so much.